طيب بسم الله والحمد لله والصلاة والسلام على رسول الله وعلى آله وصحبه وله. I'd like to welcome you all to this first lecture of ICS 254, the first lecture in week 3 of ICS 254. I have a couple of announcements first. The first one is regarding the office hours. As you might have seen last week, I have posted I have made a team that includes all the students from both courses, ICS 104 and ICS 254. I'm teaching the two courses this semester. So I will be using this room. It will be open basically during the office hours. So all what you need to do is just when you join the room, you're asked, to say hi or hello, because usually I will not, unless somebody is with me, talking, I will not be using the camera or having the mic on. So just, say hi and wait, a few seconds until I, unmute and reply. I think this is much better and more formal for the office hour. So this is regarding the office hour. Regarding the quiz, inshallah, we will have our first quiz on Wednesday. And I will basically let you know the details, whether next lecture on Tuesday or when, through announcement or, through announcements. The material will be basically what we covered in the previous 2 weeks, okay? So until before this section 4.3, which is primes and greatest common devices. Okay, Shabab? Right. So any question before we proceed? No questions? Very good. Okay, so last time, basically what we did was we looked at the modular, modular exponentiation algorithm to basically find the any value which is raised to a certain exponent mod another value. We saw an efficient, algorithm to carry that out. So now we will move on to section 4.3, which will talk about prime numbers and greatest common devices and greatest common devices. So let's start with this definition. An integer p is greater than 1. An integer p greater than 1 is called prime if the only positive factors of p are 1 and p. Okay? A positive integer that is greater than 1 and is not prime is basically called composite. Okay? So we define an integer to be called a prime if it is greater than 1 and the only positive factors of that number is 1 and itself. Okay, is 1 and itself. We say that this is a prime number. And I think maybe we mentioned this before. The smallest prime number is
2.
The smallest prime number is 2. Okay, the smallest prime number is 2. Right. Okay, so let's look at these questions. In the other section, we solved A, C, and E. So let us solve B, D, and F. Okay, let us solve B, D, and F. So let's start with B. Determine whether each of these integers is prime. Okay, so 29. What do you think? Is it prime or not prime?
Prime.
prime.
It's a prime, صح? 29 is a prime number. So this is a prime number. Okay. طيب. What about 97?
It's also prime.
It's also prime.
I think it's not prime.
It's not prime. So what drives you? If you think that it is not a prime, you need to tell me which number does it divide, صح?
I might be wrong, but could be. Oh no, never mind. I tried my method. It was wrong.
It was wrong. Right. So in fact, it is true that 97 is also a prime number. Okay, 97 is also a prime number. طيب, what about 143? What about 143?
Not prime.
Not prime? So what does it divide?
For example,
No,
13.
it is prime.
13? So let's check. So 143 divided by 13 is 11. Huh? Right?
Yes.
So 143, this is equal to 11 multiplied by, is equal to 11 multiplied by 13, right? So although it looks like a prime, but it turns out that actually it is not a prime number, right? It is not a prime number. So this is not a prime number. In fact, we will see a theorem that will make, determining prime numbers to be a little bit easier than, what would you do if you want to check whether a number is prime or not? Let me ask you this question.
Find a number divides.
Check the number smaller than the square root of the number.
Squarer than the square root. Well, this is the theorem that we will see.
Factorize it. Try to factorize.
Try to factorize. Well, how do you try to factorize it?
Try to guess two numbers that are, when you multiply them, they will be equal to the number.
But don't you think that this is harder than trying to find a single number that is a factor of it?
Yes. But it's
it's easier to try to find. It's easier to find a number that divides it than trying pairs. Huh? Than trying pairs. So now based on maybe your what many of you might think, for 143 I will say, okay, then I will check 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe until I reach what, 142 or 140 or whatever, right? One of you mentioned that we need to do it only for the square root, and he's correct, and inshallah we will actually prove that theorem. Okay, we will prove that theorem. Okay, fine. Good. So let's come now to the first theorem today, which is called the fundamental theorem of arithmetic. Now, the theorem says the following: every integer greater than 1 can be written uniquely as a prime or as the product of two or more primes where the prime factors are written in order of non-decreasing size. In order of non-decreasing size. Right. So, in a nutshell, what does this theorem say?
that you can write every integer in terms of prime numbers.
In terms of prime numbers. How?
By factoring.
By fact. No, this is not what I meant. So basically, every integer greater than 1 can be written uniquely as. Now, here you can see two cases. The first case is as a prime number. Right? Or, now where do we go to the second case?
Product of two primes.
Well, no, more general. If it
If
was not a
the
prime,
number, yes.
if the number was not a prime number, okay? So if the number was not a prime number, then we can write it as the product of two or more primes, where the prime factors are written in order of non-decreasing size. The prime factors are written in order of non-decreasing size. Now, what does it mean, non-decreasing size? What does it mean, non-decreasing size?
maybe increasing.
increasing. لا مش increasing. هي opposite of non-decreasing. Opposite of decreasing. Non-decreasing is opposite of decreasing. So what is the opposite of decreasing? It's either steady or increasing. Steady or increasing, صح? This is called non-decreasing. Let me give you an example. If you consider, for example, a 12, what are the product of primes that 12 consists of, in which I can, order them in non-decreasing order?
2 multiplied by 2 multiplied by 3.
2 multiplied by 2 multiplied by 3, right? So the second 2 here, the second 2, is it bigger than the previous 2?
No.
So it's not increasing, huh?
Yes.
It is not increasing. يعني from here to here is not increasing, but from here to here it's increasing, from 2 to 3. That's why we call it, in this case, non-decreasing. Okay, we call it non-decreasing. واضح يا شباب؟ طيب. So again, the theorem says if I have any integer greater than 1, then it's either a prime number, or if it is not a prime, I can write it as a multiplication of prime numbers ordered from the smallest to the to the highest, or in order of non-decreasing size. In order of non-decreasing size. So let's take this example, and then we will prove it. Okay, let's take this example, and then we will prove it. So it says here, find the prime factorization of 10 factorial. Now, how do I find the prime factorization of 10 factorial? What do I need to do first?
Write the factorial, like 10 multiplied by 9.
Exactly. So I'm going to write first 10 factorial is equal to 10 multiplied by 9 multiplied by 8, 7, 6, 5, 4, 3, 2, and then 1. Okay, so 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right. Next. So I wrote 10 factorial. So now how can I find?
Factor every number, like 9 to 3 multiplied by 3.
Every number, ولا نقول every composite number?
Every composite number can be written as a product of prime numbers.
Exactly. So the 10, we will write it as
5
5 multiplied by 2.
5 multiplied by 2
multiplied by
9
3.
3 multiplied by
3
3.
by 3.
اللي هي 3 سكوير. ايش رايكم؟
Mm,
وال8
2
2
cube.
to the power 4.
to the
أو
power
cube.
3
Sorry.
to the power 3. طيب 7 برايم صح؟ 6
Yes. 3 multiplied by 2.
3 multiplied by 2
5 prime.
طيب
2 to the power of 2.
Choose both.
And the
Three
rest are primes.
2 prime 1 prime.
do I have to write 1?
No.
I
No.
don't have to. لأنه 1 is not considered a prime number. Okay? 1 is not considered a prime number. طيب next. Next, what do I do?
Collect or group the similar prime numbers to
Yeah,
the
be-
same power. So
yeah,
you have
because-
3 and 3 and 3.
Because it says here, prime factors are written in order of non-decreasing size.
Yeah.
Right? So what are the prime factors here that you can see?
2 and 3. We have
2, 2
3.
multiplied by 3. أيوة.
5 and 7.
5 and 7. Do we have any other prime number?
No.
No.
No, we don't. Type. Okay, so now 10 factorial is equal to, now I need you on the chat to write what is the exponent of 2, the exponent of 3, the exponent of 5, the exponent of 7. What are the exponents of 2, 3, 5, 7? I should say 2 to the power what multiplied by 3 to the power what multiplied by 5 to the power what multiplied by 7 to the power what? Okay. 2 to the power 8 multiplied by 3 to the power 4. خلينا نشوف أول واحد كتبها تقريبا. طيب ماجد he says 7421. راجع نفسك يا ماجد. طيب let's check مشعل what he says. 2 to the power 8 multiplied by 3 to the power 4 multiplied by 5 to the power 2 multiplied by 7. Multiplied by 7. So basically he says 2 to the power 8, 3 to the power 4, 5 square, and of course 7 to the power 1. So let's check it. Let's check it. So how many 2's do we have? Well, let's start from the right. Okay. So basically we have 1, 2, 3, 4, plus 3, 7, plus the 1 of the 10 is 8. So we have 2 to the power 8. طيب, the 3, we have 1, plus 1, 2, plus 2, 4, and that's it. So we have 3 to the power 4. For the 5, we have 1, and then 1. So this is 2. And finally, the 7, how many 7s do we have? We have only 1 7. So 7 to the power 1. Okay, 7 to the power. Any question, ya shabab? So basically, notice here that what we have done is we have written 10 factorial as the product of how many primes? Well, if you sum the top 15 primes ordered, using a non-decreasing size. واضح يا شباب؟ طيب. So now let's come to the proof. Now let's come to the proof. How do we prove that every integer greater than 1 can be written uniquely as a prime or as a product of 2 or more primes, where the prime factors are written in order of non-decreasing size? Well, it turns out that we can use a proof by induction, okay? We are going to use the proof, we're going to use induction. So proof by, now let's see. What are the types of induction that you have covered in ICS 253?
Strong and weak inductions.
Strong and weak induction. طيب. What's the difference between strong and weak induction? Weak, by the way, is also called mathematical induction. Weak is called mathematical induction. So what is mathematical induction and what is strong induction?
Mathematical induction use basis step and inductive step.
طيب. والstrong induction.
The difference is for the mathematical induction, we assume that k equals to something like is true. But for the strong, all the numbers until k are true.
Okay. So let me, by the way, this lecture is going to be a very good review, of proof techniques in general, because we are going to see maybe 3 different proof techniques today. Okay. We are going to see 3 different proof techniques. So in mathematical, so in induction, as we said, we have 2 types of induction. We have mathematical and we have a strong. Now, the mathematical or the weak induction, in the proof of it is as follows. You first have a basis. Then you assume that the result holds for n, and you show it for n plus 1. Okay? You assume that the result holds for n, and then you show it for n plus 1. In strong induction, again, you will do the basis, but instead of going only from n to n plus 1, you will say, well, I'm going to assume that the induction works, or the hypothesis works for all values that are less than or equal to n and greater than or equal to 1, 2, a certain number. Okay, so we assume that it works for all of them, right? And then we show it for n plus 1. Right. My question to you now is, in your opinion, which one are we going to use? The strong induction or the mathematical or the weak, the mathematical/weak induction? And I need somebody to tell me why.
You say strong?
You say strong. ليش يا ماجد strong?
Because for like when we have a big number, we need to prove that, as we did in the exam, and the example just now, all the previous numbers has to be like written in prime or a multiple of primes. So we need to prove all the way through till that number.
Well, kind of. So what's wrong with mathematical induction or weak induction? What's wrong with mathematical induction?
It will only prove that n plus 1 is true, not all the numbers that...
Well, this is not what you meant to say. What you meant to say is it only assumes that it holds for n.
Yeah.
not for n minus 1, n minus 2, n minus 3 صح؟
Exactly.
طيب. Now the thing is is there any relationship as far as prime numbers or whether it is a prime or not or composite or not between n and n plus 1?
There is n.
Between n and n plus 1. Do we know any information about prime, not prime, things like that between n and n plus 1?
If it was one type, it will be the other. Like if it was prime, if we plus one, it will be not prime.
طيب يعني مثلا ال5 is a prime صح؟ ال6 is
Not prime.
not prime. طيب 7 is
Prime.
prime. ال8 is
Not a prime.
not prime. ال9 is
Prime.
Not prime.
ال9 is
Not prime.
Not a prime.
not a prime.
But you
ال10
can
is
conclude that if n is prime,
Not a
n
prime.
plus 1 is not prime.
if n is prime, n plus 1 is not prime. Yes.
Yes, this is for
Yes.
sure.
Yes, this is for sure. Right? Except for 2, صح?
Yes.
Except for 2, this is for sure that if n is prime, n plus 1 is prime. But the problem is the other way is not necessarily true. If we know that n is not prime, n plus 1 has nothing to do they're kind of different. We saw examples when n plus 1 was prime, we saw examples when n plus 1 was not prime for the same case. Not prime. If n was not prime, n plus 1, in some cases it was prime, in some cases it was not. So that's why it's going to be very difficult to use mathematical induction, because there's really no relationship between n and n plus 1 with respect to prime numbers and factors and things like that. But if we use a strong induction, we will notice that there is a big connection. Okay, we will use that. We will, know that this is has a big connection. So let's use strong induction and let's start with the basis. Now, what is the basis? n equal ايش? Remember يا شباب, this is what we are trying to prove. Every integer greater than 1 can be written uniquely as a prime or as the product of 2 or more primes. By the way, we are going to only prove existence. Uniquely, we are not going to, it's up, I'm going to leave it for you to prove the uniqueness, okay? To prove the uniqueness. And I think it's in the book, and maybe it's one of the odd numbered exercises, if I'm not mistaken. Okay? طيب. يلا يا شباب. ايش البيسس؟
2 is prime.
n equal 2 صح؟
Yes.
n equal 2 and 2 is a prime number. 2 is a prime number. Done ولا مش done regarding the basis?
Done.
Done, because that's what we want to show. We need to show it's either a prime or product of primes in non-decreasing order. بس. Okay, so we are done with the basis. So this is a prime number. Right. Now let's look at the induction step. The induction step. Right. Who is gonna tell me what will be the the induction hypothesis in this case? What is the induction hypothesis?
It will be 2, 3, 4, all the way to n.
أيوة.
Are prime or multiple of primes.
Are primes or multiple of primes, and we want to show that
n plus 1 is prime or a multiple of prime.
Excellent. And we want to show that n plus 1 is a prime or a multiple of prime. So for the induction, we will say assume that the result holds for k greater than or equal to 2, less than or equal to n. Okay, where k and n are positive. Assume that the result holds for k greater than or equal to 2, less than or equal to n. طيب. So what does that mean? i.e., the result i.e., let's say each value integer value that is each integer value k between brackets k greater or equal to 2, less than or equal to n. K is prime or a product of primes. This. Okay, so this is my induction hypothesis. Assume that the result holds for k between 2 greater than or equal to n, i.e. that each integer value k, where k is between 2 and n, k is a prime or a product of primes. K is a prime or a product of primes. What do we need to show? يلا يا شباب. To show that
N plus 1
is
prime or a product of primes.
exact. To show that n plus 1 is a prime or a product of primes in non-decreasing order. Okay, show that n plus 1 is a prime or a product of primes in non-decreasing order. Right, how do we continue? So this is my induction hypothesis, and this is what I need to show. So the question is now how to proceed. Right, let me help you. So what do we want to show? To show that n plus 1 is a prime or product of primes in non-decreasing order. Right. Now, so what I'm going to say is the following. There are two cases. For n plus 1. What is case 1 يا شباب?
If n is not prime.
If n is not
Prime.
ترى notice that we are talking about n plus 1 مش n.
Yeah, but I mean, if n was prime, then n plus 1, not prime, I mean, then n plus 1 will be prime, no?
Hint. The first
n plus
case
1 is
is the easy case.
n plus 1 is a prime.
N plus 1 is the prime. احنا يا شباب, what do we want to show? هيها مش this is what we said, that we assume that K is prime or a product of primes to show that N plus 1 is a prime or a product of primes. That's what we want to show. So if N plus 1 is prime, we are done, صح?
Yes, it's already a prime, so no need
خلاص.
to prove it.
خلاص, it's already prime. If N plus 1 is a prime, we are done. كفى الله المؤمنين القتال. خلاص, N plus 1 is a prime. The problem is case 2. What is case 2? If N plus 1
It's not a prime.
is, and what is not a prime? The opposite of not a prime is?
Multiple of
No, composite, yeah.
Exactly. Case 2, if N plus 1 is composite. طيب. Any ideas how am I going to continue? Think about it until I get a bottle of water. Just a second. أيوة يا شباب.
show it that it's multiple of prime.
If N plus 1 is composite, so what do how do I continue? What did you say?
Write it in multiple of prime, or
We want to write it as multiple of primes. طيب, how do I know no, they are multiple of primes? Hi يا شباب, what does it mean N plus 1 is composite?
Two. There is two. Two multiplied by something.
2 ليش 2؟ افرض ال N plus 1 equal 9. افرض ال N plus 1 is 9. And 9 is 2 multiplied by something?
No.
No. So if N plus 1 is composite, the only thing that I can conclude is if N plus 1 is composite, then there exists M1, M2, and Z plus such that the M1 and the M2 are greater than or equal to 2, less than or less than basically N plus 1, less than N plus 1, such that less than N plus 1, such that M1 multiplied by M2 is equal to N plus 1. Right or wrong? Isn't this what N plus 1 composite means? Do we know, by the way, M1 is prime or M2 is a prime?
No.
We don't. We don't know whether M1 is prime or M2 is prime. Okay? We don't know whether M1 is prime or M2. All what we know is, since N plus 1 is composite, that, you know, we can multiply, that we can get N plus 1 by multiplying two numbers, and these two numbers are greater than or equal to 2 and strictly less than N plus 1. And strictly less than N plus 1. Okay? Which means that, you know, M1 is greater than or equal to 2, less than or equal to N, while M2 is greater than or equal to 2, less than or equal to less than or equal to n. Okay. طيب, anybody any idea for continuing? Hint. We need to use the induction hypothesis. Where are we going to use the induction hypothesis?
There, the K is the M1.
K ولا M1?
Yeah, it is like in the same position.
M1 and M2, صح ولا لا? Because M1 is greater than or equal to 2, less than equal to n. Well, M2 is greater than or equal to 2, less than or equal to n. Right? So I can apply. So because of this here, I can apply my induction hypothesis in any number that satisfies this inequality. And both of them satisfy this inequality. Both of them satisfy this inequality. So therefore, M1 can be written as, P1, P2, up to PR, R and Z plus, and M2 equal Q1, Q2, QS, again, belong to Z plus, such that therefore M1 is P1, P2 up to PR. Yeah, such that P1 is less than or equal to P2, less than or equal to PR, and Q1 less than or equal to Q2, less than or equal to QS. صح ولا لا يا شباب؟ This is by induction hypothesis. طيب, وبعدين يا شباب, next.
Maybe multiply P by Q.
P by Q ولا M1 by M2?
Which is basically all the P's
Yeah.
multiplied by all the Q's.
Yeah. So therefore, n plus 1, which is equal to M1 times M2, is equal to, P1, P2 up to PR, Q1, Q2 up to QS. Up to QS. طيب, can I rearrange the P's and Q's such that they start from the least, from the smallest to the highest, or in non-decreasing order?
They are already in order, I think.
I don't. Well, they are all in order as a whole. But how do we know that PR is less than Q1? يعني this could be
maybe
يعني this could be
P1.
مثلا this could be 2 times 3 times 5. Or this one is 2 times 7 times 9. 9 مش 2 times 7 times 11. واضح? So I just need to rearrange them. Right? So therefore, n plus 1 is a product of primes that can be easily ordered from smallest to highest. Okay, that's it. خلاص. We're basically done. So now I have written M1 times. So if n plus 1 was not a prime, I was able to write n plus 1 as a product of primes. Alaykum assalam. I was able to write n plus 1 as a product of primes from the smallest to the highest. Okay, from the smallest to the highest. So this is proof by strong induction of existence only. Of the existence. So uniqueness, as I said, you can read it. I think it's a solved problem in the textbook. I think one of the odd exercises. Yeah. It might be not. It might not be here. It might be in chapter 5. Okay. Might be in chapter 5, and the exercise also might be in chapter 5, which is basically the chapter on induction. واضح يا شباب بالنسبة للبروف. So if I bring it in the
It's
in
a
the
bit
midterm.
messy, but يعني we will need to revise it one or more times to comprehend it very well.
Yes. Yes. Okay. Right. But the idea is very simple. Okay. I think يعني I don't think it's a problem. Okay. Right. So now we come to what one of your colleagues mentioned in the beginning of this class, that how do I know if a number is prime or not? He says, well, I can check the whether it is divisible by its square root until when I reach 2, right? Until when I reach 2. So let's first prove the theorem, and then we will come to the example. Okay, let's first prove the theorem, and then we come to the example. So the theorem says, if n is a composite integer, then n has a prime divisor less than or equal to square root of n. Then n has a prime divisor less than or equal to square root of n. Fine. So what do you think we are going to use to prove this theorem? What do you think we are going to use to prove this? Do you think we're going to use induction? Do you think we're going to use induction, ya shabab? No idea?
Maybe
No,
not induction.
there isn't, because it's less than or equal. So it's
doesn't seem like induction. Fine. In fact, the method that we are going to use for the proof is actually we're going to use the proof by contraposition, or contrapositive proof. Okay, so this is proof by contraposition. Now, who can remind me what is the proof by contraposition?
I think you assume that something is wrong and then prove that it's not wrong. Something like that.
حرام عليك.
If P implies Q,
أيوة.
then prove Q implies not P.
لا. This is not
not Q implies not P.
Not Q implies not P. If I want to show that P implies a Q, then I can do that by showing not Q implies not P. So what is P and the Q in this case? Well, P is if n is a composite integer, صح? This is P. What is Q? Q is n has a prime divisor less than or equal to square root of n. This is Q. Okay, right. Now I need somebody to tell me what is not Q. What is not Q?
has a composite divisor.
Has not a prime
ايوه
device.
مش composite. N does not have a prime divisor less than or equal to square root of n. Okay, so this is what we will start with. So assume that, so by contraposition, what does that mean? Assume that n does not have a divisor that is less than or equal. ما انكتبت صح.
A divisor or a prime divisor?
Prime divisor مظبوط. That has a prime divisor that is less than or equal to n, to square root of n. صح؟ Okay, that's my wife. Now we need to go back to the lecture. I hope. Okay, very good. طيب. So let me do this. Now nobody can call me. طيب. Okay, so assume that n does not have a prime divisor that is less than or equal to square root of n. So this means that i.e. all prime divisors are ايش؟ يلا يا شباب. All prime divisors are
Greater than
square root of n. All the prime divisors are greater than square root of n. طيب. Now my in particular, there exists P1 and P2 prime numbers أو prime divisors خلينا نقول, because we want them divisors. Prime divisors such that P1 is greater than square root of n and P2 is greater than square root of n. طيب, my question is, why can I assume this? مش هنا قلنا all prime divisors are greater than square root of n. طيب, my question to you is it possible that I have a single prime divisor? Is it possible that I have a single prime divisor?
No.
Why not?
One.
It has to be two things multiplied by each other.
It has to be two. طيب, why not one? Just one prime divisor.
If it's 1, it's multiplied by itself, so it's n, and that's not what we said. We said that's not less than, or it cannot be less than or equal to n.
لحظة شوي. احنا هنا قلنا assume that n does not have a prime divisor that is less than or equal to square root of n. Now we're doing the contrapositive now. So my question is, why do I have two? Why I can't say, you know, there might be only one? Hint.
Because it has to be multiplied by another thing.
Because it's not a prime, it's composite. If we said we only have one prime number that is one prime divisor that is greater than square root of n, then it's basically the same. It is a prime number, صح? It will be greater than square root of n. It will be n itself. And it will be prime. It will not be composite. And now we are saying, you know, n is composite, right? We are saying that n is composite. So that's why we can assume that there might be more ترى. يعني يكون في P3 و P4 و P5 بس أنا all what I need is only two. Two are more than enough. So I have now two prime numbers that are greater than square root of n and are divisors of n, right? And are divisors of n. طيب. Can anybody see now where is the contradiction or what's the problem?
If P1 multiplied by P2 is greater than square root.
Is greater than ايش؟
Square root of n. Or n, because P1 is greater than square root.
صح؟
Yes.
P1 greater than square root of n. Will P2 greater than square root of n. معناته P1 multiplied by P2 is greater than square root of n multiplied by square root of n, which means إنه P1 times P2 is greater than n. صح؟ So this means that we can only have one such prime number, i.e. n equal, you know, P1 is a prime number. And this basically concludes our proof. Okay, so I started by saying that n does not have a prime divisor less than or equal to square root of n, and I showed that n is prime. And I showed that n is prime. This, by the way, can also be proven by contradiction. Okay, you assume that, you know, n does not have a prime divisor less than or well, I think no, contrapositive is fine. Okay, contrapositive is fine. So we started from not Q and we showed not P, and we showed not P. Okay, right. Now after we have done this theorem, can anybody tell me how does this theorem gonna help me to determine whether 101 is prime or not? محمد الهاشم، وينك يا محمد؟ من زمان ما سمعنا صوتك.
Yes, doctor.
When how do I know, or how can I find out 101 is prime or not using this theorem?
We take the square root.
Okay.
101
Okay, so since the square root of 101 is what? Is approximately
10
point something, صح?
Yes.
We know that you know, if it was composite, it will have a divisor between a prime divisor, between 2 and 10. صح ولا لا؟ If it was composite,
Yes, yes, between 2
then
and 10.
it has to have a prime divisor between 2 and 10. Right. So what are the prime divisors between 2 and 10?
You have 3, 5, 7.
Since the prime divisors are with 2 طيب.
Yeah, 2 included.
Between brackets, you know, between 2 and 10, it is obvious that none of them is a divisor of 101. 101 does not divide 2 without remainder. Why is it clear that 101 does not divide the 3?
Because the sum of the numbers.
The sum of the digits, صح?
Yes.
1 plus 1 is 2, is not divisible by 3. By the way, إحنا إن شاء الله you will prove this, by the way. You will prove that if you have a number in which the sum of the digits is divisible by 3, that, you know, it is the whole number is divisible.
The whole number is divisible by 3. If it's not, it's not divisible.
Yes. So you will show that. طيب. 5, it's obvious it is not 5. صح? The only one left is 7. So for 7, if you just come here, you say 101 divided by 7. This is basically 1. From 7, this is 3. 31 divided by 7 is 4, right? So there is basically 28, 31. So basically we have 3 as a remainder. We have 3 as a remainder. So this means that, you know, none of them is divisible. So n is prime. Okay, or 101 in this case is prime. Any question, ya shabab? Any question? طيب. Okay, so let's look at this sieve of Eratosthenes. Now, the sieve, you know what does sieve mean? تعرفوا المنخل يا شباب؟
ايوه.
المنخل. You know, if you want to, if you have, you know, some, you know, small things and you want to remove the bigger ones, you just put it in what we call a sieve, right? This is the idea behind the sieve of Eratosthenes to find the prime numbers, for example, between 1 and 100. To find the prime numbers between 1 and 100. What it does is the following. First, I will start with the smallest, you know, number that is divisible by, that is a prime number, which is 2, right? And what I will do is I will underline all multiples of 2. So as you can see here, all the multiples of 2 are underlined. Now, what does that mean? This means that I'm excluding those numbers from possibly being prime numbers. So this will remove all even numbers. Okay, this will remove all even numbers. Okay, until I reach 100. Okay, until I reach 100. طيب. Next, what do I do? what is the number after 2 which is not underlined? The number after 2 which is not underlined is 3. Well, this means
Which
that
is a prime.
This means that 3 is a prime number. So now what do? Repeat. Instead of multiples of 2, now we are going to, remove multiples of 3. صح? So now we are going to underline the 6, which is already underlined, underline the 9, underline the 12. Yeah, underline the 9. Why do I have only one line under the 9? Because it was not underlined before, صح?
It was not. Yeah, it was not a multiple of 2.
It's not. 2 is not one of the divisors. It was underlined only one time. 12,
What
no.
8, teacher?
8 is a multiple of 3.
No,
It should be underlined from before, from 2.
It should be underlined from 2, and it is already. I think this is a mistake by the from the book. I think. Let me just do this. تزوير في أوراق رسمية. Okay. Oops, what happened? Right, let me open it again. I just hope that we don't mess it up again. Okay. So now, as you can see here, we have 9 and then 12, 15, only one line. Okay. 18, we have 2 lines for 18. 21, 1 line, and so on and so forth. So it will remove the multiples of 3s. Right. Now, after we remove the multiple of 3s, what is the next integer greater than 3 and not underlined?
5.
You will go to 5. Okay. So now when you come to 5, now you will underline multiples of 5. 10 is already seen. 15 is already seen. What do you think the first number that has only one line, which is a multiple of 5? The smallest one.
25.
Hey, 25. Right? 25, because 25 is basically the only divisor or unique because it's 5 squares. Huh? 25, and of course 30, 35, 40, 45, and so on and so forth. Okay, so we are done with 5. طيب, next. Well, next, what do we have? We have the 7. صح? Next, we have the 7. So we remove multiples of 7. What is the first multiple of 7 that will have only one line underneath?
Yeah, 49 maybe.
49, huh?
Yeah.
49. So 49 is the only one. And after we carry it out for 7, whatever that is not underlined is ايش? Whatever
is a prime.
Is a prime number. Whatever has not been underlined is a prime number. Why don't I need to continue like to reach 11 مثلا? We took it in just a few seconds. Remember,
because it will be above 100. 11 multiplied by 11.
Because square root of 100 is 10. So once we reach 7, the next prime number is 11. There is no need to apply this because خلاص, we have already reached, greater than the square root of 100. So we're sure that, all the composite numbers have been removed. We are sure that all composite numbers have been removed. Okay, شباب? So this is the last thing that we will do today, which is basically cardinality of the set of primes. Okay, cardinality of the set of primes. What do we mean by cardinality? هي السايز أخذتوها بشابتر 2 in ICS 253. Yes. So what is the cardinality of the set of prime numbers? Well, it says here that there are infinitely many primes. There are infinitely many primes. How do we prove it? Well, we are going to prove it by contradiction. Okay, we are going to prove it by contradiction. So what do we need to do in order to do that? Well, let's assume, since we are going to use contradiction, let us assume that, so proof here by contradiction. Okay, so let us assume that the number of prime numbers is finite. Or the cardinality of the set of prime numbers is finite. Okay, i.e., that assume that خلينا, I think it's better to say the set of prime numbers. So the set of prime numbers, and let's call it S, is finite, i.e., assume S is equal to, because it's finite, I can list them, P1, P2, up to Pk. Okay, I can list them. Finite. Right. Now look at what I'm going to do. I'm going to construct the following number, and then you tell me what that number is. Okay. Right. Let n in Z such that n is equal to, look at what I'm going to do, P1 multiplied by P2 multiplied by P3 all the way multiplied by Pk plus 1. So I have constructed a new number, P1, P2, P3, P4 up to Pk, and then added 1 plus 1. Right. First thing is the number n is prime ولا not prime? Hello?
Not prime.
Not prime. Why not?
Because we said when we have a prime number with plus 1, it won't be prime unless it was like 2.
No.
Prime number plus 1 is not prime.
No, that's well, who said P1 multiplied by P2 multiplied by Pk is a prime number?
It's multiplied, sorry.
Yn is not prime. He's right. N is not a prime number. But Yn is not a prime number?
Because it's multiple of primes. No?
A multiple of primes cannot be a prime number. Aslan, this is the definition of composites, huh? But this is not, so this is P1, P2 up to Pk plus 1. The number n is composite since n does not belong to S. Didn't we say that the number of prime numbers is finite يا شباب. Will n, isn't n greater than any number in S? I multiplied positive numbers plus 1. So n is not in S, definitely. And I said that the number of prime numbers is finite, not infinite. So I put them all in this set, and then I, formed P1, P2 up to Pk plus 1 as a number. This is a composite number. طيب. If this is a composite number, doesn't that mean there exists an integer I greater than or equal to 1, less than or equal to k, such that pi divides n. مظبوط ولا لا يا شباب؟
Yes.
Yes.
Because n is composite.
Mm-hmm.
So there is a prime number that divides n, صح؟
Yes.
طيب ال pi divides n. Will pi, does it divide p1, p2 up to pk?
It should not, right?
It should not. If it should not.
No, it divides because it's a multiple of the multiplication of them is n, so it divides n. If it divides n, it divides p1, p2, p3, and so
لا ترى divisibility of pi or p1 pi is a divisor of p1 p2 up to pk has nothing to do with n. يا شباب ترى ال pi is one of them ولا مش one of them؟ one of these pi's ولا لا؟ معناته divides ولا ما does not divide؟ divides. It's one of them. I is one of them. Okay, so pi divides n, and pi divides p1, p2 up to pk. Therefore, pi divides what? If it divides n, or divides p1, p2 up to pk, shouldn't it divide 1? صح ولا لا يا شباب؟
Yes.
والله it should divide 1. We took a theorem earlier that if p divides, what was it? C divides A and C divides B, then C divides A plus B, or A minus B, it doesn't matter. So here, Pi divides N, Pi divides P1, P2 up to Pk, so therefore Pi divides N minus P1, P2 up to Pk. However, P1 N minus P1, P2 up to Pk is nothing but 1, which is a contradiction. There is no integer greater than 1 that divides 1. Okay? There is no integer greater than 1 that divides 1. Any question يا شباب? Any question? So inshallah then let's stop
we
here.
have a request
تفضل.
if we may, not if you can, if it's possible that you upload some